In this video series subset, we'll look at 3 different hydrogen pathways in the HDSAM model, the first one being liquid hydrogen. I'll review the scenario worksheet to identify the liquid hydrogen selection options. Then I'll walk through the structure and inputs of the 3 liquid hydrogen worksheets. And finally, I'll demonstrate some examples. As a reminder, HDSAM incorporates economic data into the energy and emissions modeling provided through GREET to enable assessment of financial sustainability as well as environmental sustainability of hydrogen delivery pathways. In HDSAM, the liquid hydrogen pathway begins at a centralized gaseous hydrogen production facility, after which gaseous hydrogen is compressed and pumped to a liquid terminal. From the liquid terminal, the now liquid hydrogen is transported via liquid hydrogen truck to a refueling station where the fuel is dispensed to vehicles. On the scenario worksheet in the model, there are some market demand selections, delivery mode selections, a refueling station capacity selection, and storage options. The selections for the liquid hydrogen pathway include the liquid H2 truck for the transmission and distribution modes, and liquefier and liquid storage for the storage option. At the top of the H2 liquefier worksheet are some tables showing the calculation outputs from the sheet, as well as energy use and emissions resulting from the process. The primary outputs in these tables are the portion of total real levelized delivered hydrogen cost from the liquefier process, the broken out capital and energy fuel cost contributions to that liquefier portion, as well as system energy use and the real after-tax discount rate. The first table is for liquefier design inputs. The main input here is the drop-down menu regarding default liquefier electrical energy consumption. The second table is for liquefier scenario inputs, with the main input of interest being hydrogen loss during liquefaction. After a table containing calculated values is the economic assumptions table. Inputs required in this table are liquefier lifetime, state taxes, and federal taxes. Next, there are a couple of tables related to capital investment. There's an optional input in the first table for user input installed costs, and in the second table there are required inputs for land costs and other capital costs. The table that follows contains O&M costs. The significant inputs here include labor cost, electricity cost, insurance, property taxes, licensing and permits, operating, maintenance, repairs, overhead and G&A, and other fixed operating costs. The remaining tables contain all calculated cells. Moving to the liquid H2 terminal worksheet, you'll notice that the structure looks the same as that of the H2 liquefier worksheet. At the top, we find the calculation outputs, energy use, and emissions resulting from the process. The primary outputs in these tables are the portion of total delivered real levelized hydrogen cost from the liquid hydrogen terminal process, the broken out capital and other cost contributions to that terminal portion, as well as system energy use and the land required for the terminal. The first table is for liquid H2 terminal design inputs. The main inputs here are number of backup pumps, maximum cryo pump throughput, maximum volume of single storage sphere, and storage boil-off. The second table is for liquid H2 terminal scenario inputs, and the main inputs in this table are minimum number of days of storage, time required per fill, and time required for parking, connection, disconnection, and removal of trailer. After a table containing calculated values is the economic assumptions table, where the significant inputs include pump lifetime, storage lifetime, inflation rate, state taxes, federal taxes. Next, there are a couple of tables related to capital investment. Looking primarily at the second table, the required inputs here are land cost, other capital cost, and then in terms of percent of initial capital investment, there's site preparation, engineering and design, project contingency, one-time licensing fees, upfront permitting costs, and owner's costs. The table that follows contains O&M costs. The inputs of interest here include labor cost, utility costs, electricity consumption, electricity cost, total electricity cost, insurance, property taxes, licensing and permits, pump and storage operating, maintenance and repairs, overhead and G&A, and other fixed operating costs. The remaining tables contain all calculated cells. Again, on the truck LH2 delivery worksheet, the structure will look familiar. The primary outputs in the calculation outputs table are the portion of total real levelized delivered hydrogen cost from the truck delivery process, the broken out cost contributions to the process from capital, energy and fuel, and other costs, as well as system energy use. In the first inputs table for liquid hydrogen truck design inputs, the main inputs are tank water volume, tank loading losses, tank unloading losses, and tank boil-off rate during transit. The second table for liquid hydrogen truck scenario inputs has input fields for tanker usable delivery capacity, average truck gas mileage, refueling stations location, and truck yearly availability. After the calculated values table is the economic assumptions table. Again, the significant inputs include pump lifetime, storage lifetime, inflation rate, state taxes, federal taxes. In the following capital investment table, there are required inputs for the per unit costs of the truck cab and the tank trailer. In the fixed O&M costs table, the inputs of interest include labor cost rate, total labor cost, fuel cost rate, total fuel cost, insurance, property taxes, licensing and permits, operating maintenance and repairs, overhead and G&A, and other fixed operating costs. And again, the remaining tables contain all calculated cells. For demonstration, I'll run a scenario with the default inputs for a liquid hydrogen pathway, and then I'll run a few scenarios after modifying some of the inputs to the liquid H2 pathway, and then compare results to the default scenario results. I'll set up my scenario inputs on the scenario worksheet, selecting urban as the hydrogen market and choosing Sacramento as the city selection. I'll set the hydrogen vehicle market penetration at 4% and select the T&D modes to be liquid H2 truck. The dispensing rate will be 500 kilograms per day, and the dispensing option will be 700 bar gas via pump. Finally, I'll select mid for the production volume, and I'll click to run the model. The first modification I'll make is to the distance from production to city delivery input on the scenario worksheet to see what impact that has on trucking cost. Before I make the change, I'll copy the cost results for transport on the results summary sheet to preserve the default result, and that way I can compare after modifying the input. The default total cost is 28 cents per kilogram of hydrogen. Back on the scenario worksheet, I'll change the distance input from 100 kilometers to 400 kilometers, and I'll run the model again. Checking the results, we can see that increasing the trucking distance increased the total delivery cost from $6.88 per kilogram to $7.13 per kilogram. And on the results summary sheet, we see that the trucking cost increased to 53 cents per kilogram, with increases to the capital, O&M, and fuel contributions. For the second modification, I'll bring up a new model workbook where I've already run the model with my default inputs. And for this modification, I'll look at the impact on greenhouse gases resulting from changing the electricity generation technology from the U.S. average mix to the California mix on the H2 liquefier worksheet. I'll copy the default results for GHGs on the Energy and GHG results worksheet. The result for total GHGs is about 50 grams per megajoule of hydrogen. On the H2 liquefier worksheet, I'll change the electricity mix, as I indicated, and rerun the model. As a result of changing the electricity mix, total GHGs reduced almost in half to about 26 grams per megajoule, reflecting the lower carbon intensity of electricity generation in California. A couple of notes on the California mix. The first is that the emissions calculations on the H2 liquefier sheet refer to data tables on the GREET data worksheet in the model. There was some data missing for California electricity mix that I corrected for this example. The second is that those emissions calculations were also including a reduction factor of 1 million for the California mix, but not for the other electricity generation mixes. I corrected this as well. I expect these formulas will eventually be updated in the model, but until they are, be mindful of the upstream cell references when using the California electricity mix in HDSAM. For the third modification, I'll increase the liquefier capital cost to see the impact on total liquefaction cost. Again, I'll bring up a new model workbook with default scenario results and copy the liquefaction contribution results on the results summary sheet. The total cost here is $2.98 per kilogram. On the H2 liquefier worksheet, I'll overwrite the formula in cell D76 with a value of $150 million, about a 50% increase. Then I'll rerun the model. I'll copy the modified liquefaction contribution cost results to compare them with the default results. And the costs increased with about a 30% increase in total cost. For the final modification, I'll change the cost of electricity to show the impact of electricity cost on liquefaction. I've already copied the liquefaction cost contribution from the default scenario in the previous modified scenario, so I'll bring up another default scenario workbook for this last example and change the cost of electricity from 7 cents per kilowatt hour to 2 cents per kilowatt hour. The electricity cost that is referenced in formulas throughout the model is on the feedstock and utility prices sheet. And for the modeled fuel and year I'm using, I'll change the value in cell O26 to 2 cents, and then I'll rerun the model. Copying the modified liquefaction contribution cost results over for comparison, we can see that the reduction in electricity cost has had just a slight impact on our cost result, with about a 6% drop in the energy fuel cost and about a 2% drop for the total cost. So, to wrap up this video, I'll briefly recap the results we've seen through these examples. In the first example, I quadrupled the distance from the location of hydrogen production to my selected city, and that increased the total cost of transport by 87%. In the second example, I changed the electricity generation technology from the U.S. average mix to the California mix, and that decreased total GHG emissions resulting from this pathway by 47% compared to the default results that use the U.S. average mix. In the third example, I increased the liquefier capital cost by about 50%, and that increased the total cost of liquefaction by 30%. And in the fourth example, I decreased the cost of electricity by about 70%, and that decreased the total cost of liquefaction by 2%. That concludes the in-depth look at the liquid hydrogen worksheets in HDSAM. If you're interested, you can view more videos on Argonne National Lab's Hydrogen Model Suite to learn more. Thanks for watching.